Muy bien. Buenas tardes. Decía, bienvenidos a la Casa de América, muy especialmente bienvenidos al general Larry James, director adjunto del Jet Propulsion Laboratory, y a la directora de la Red Interplanetaria y gerente del proyecto de la misión Interestelar Voyager del Jet Propulsion Laboratory, la señora Suzanne Dodd. Bienvenidos. Bienvenido también al consejero de Diplomacia Pública de la Embajada Americana, señor Tuttle, que ya es un habitual de esta casa. Estuvo aquí esta mañana y está aquí otra vez ahora, lo que es una muy buena muestra de la estrechísima colaboración que tenemos con la Embajada de Estados Unidos. Y bienvenido a todo el equipo de Red del JPL y los compañeros que han venido de la NASA con nuestros dos ponentes. Decía que tenemos una colaboración muy estrecha con la Embajada porque tenemos con ellos diversos ciclos en marcha. Esta mañana hemos presentado una publicación sobre la presencia española y hispana en San Antonio con motivo del viaje de los Reyes que acaban de estar allí en San Antonio, en Nueva Orleans. O sea que, como ven, estamos constantemente en contacto con nuestros amigos americanos. Y uno de los títulos que tenemos ahora aquí en la Casa de América se titula I Have a Dream y es sobre los derechos civiles en Estados Unidos. Creo que hablando de dreams, de sueños, qué sueño más bonito que el que ha hecho realidad la NASA, el gran sueño del ser humano de llegar al espacio exterior. Y hoy celebramos un cumpleaños, el aniversario, el 60 aniversario de la NASA, que tuvo un inicio además espectacular porque a los 10 años de abrirse la Agencia Espacial Americana consiguieron que el hombre llegara a la Luna. Sin duda, una de las grandes hazañas de la humanidad, de la cual fue protagonista esta gran agencia. Una agencia que colabora estrechamente con España. Querría solamente recordar que en el 64 se construyó el complejo de comunicaciones con el espacio profundo de Madrid, el MDSCC, en sus siglas en inglés, que está en Robledo de Chabela, en la Sierra madrileña, como saben ustedes. De este centro, propiedad de la NASA, han ido creciendo desde una primera antena a las 6 actuales y desde ahí se realiza el seguimiento de vehículos y sondas espaciales que permiten a los vehículos espaciales que mantengan contacto directo y permanente con la Tierra. La NASA tiene otros socios aquí en España, tales como el Planetario de Madrid, el Centro Espacial de Canarias o el Centro Europeo de Astronomía Espacial de Villanueva de la Cañada a través de la Agencia Espacial Europea. Así que, sin más, solamente le quería recordarles que para completar esta conmemoración del 60 aniversario de la NASA, Casa de América va a proyectar el próximo lunes la película Hidden Figures, que cuenta la historia de 3 matemáticas afroamericanas en plena lucha por los derechos civiles de Estados Unidos. La entrada, por supuesto, como siempre aquí, es libre. Cuando quieran. Gracias por estar aquí y es un placer tenerlos en esta casa.
¿Está funcionando? Sí, sí. Muy buenas tardes a todos. Es un placer poder estar de nuevo aquí en Casa de América, ¿verdad? 2 veces en un solo día, pero como mencioné antes, ¿verdad? Esto es un lugar mucho más lujoso que mi oficina en la embajada, así que no me quejo estar aquí de nuevo. Es un placer poder presentarles rápidamente al director general, Larry James, a la directora Suzanne Dodd, de la JPL-NASA, que han venido de los Estados Unidos, y agradecemos su presencia, que han tomado el tiempo esta tarde con nosotros. Imagino que muchos de ustedes presentes ya han visto la información sobre sus currículos que se mandaron con invitaciones, así que no voy a entrar en eso en profundidad. No voy a hablar de sus brillantes carreras profesionales, porque si hiciera eso yo me sentiría mucho menos de lo que soy y quiero salir de aquí con cierto nivel de confianza, ¿verdad? Así que voy a evitar darme cuenta de lo que no he logrado. Ambos de ellos han ganado con su esfuerzo y conocimientos alcanzar puestos de gran responsabilidad, como sabemos, en NASA y debemos decirles que admiro tanto su trayectoria profesional como envidio el hecho de que trabajan para la agencia del gobierno de los Estados Unidos más popular y con mayor prestigio mundial, la NASA, que lleva ya 6 décadas alimentando los más ambiciosos sueños de la humanidad y alcanzando con sus misiones hitos inimaginables. Quiero también agradecer a la Casa de América, y muy en particular en este caso a Fernando Fernández Arias, el interés en organizar esta sesión para conmemorar el 60 aniversario de la NASA. Este es un año lleno de aniversario 60, también es el 60 aniversario del programa Fulbright entre los Estados Unidos y España, así que voy a recordar ese número 60. Los cumplo dentro de poco, pero no voy a decirles precisamente cuándo. Casa de América es un ejemplo, es probablemente la fundación que mejor evidencia en España las intensísimas relaciones existentes entre los países americanos. Como institución abierta y plural que se ha convertido en un lugar de encuentro obligado para cualquier cita importante aquí. Por eso deseo expresarle al señor director Santiago Miralles y todo su equipo el agradecimiento de mi embajada por acoger este evento y muchos otros. Yo, personalmente, me crié en California, muy cerca del Jet Propulsion Laboratory, donde trabajan nuestros invitados especiales, o como se diría en español, según la traducción mía, ¿verdad? El laboratorio de propulsión a chorro, que me suena bien chulo, ¿verdad? Laboratorio de propulsión a chorro, ¿verdad? Me gusta cómo suena. Así que impactó mucho mi infancia y juventud, y esas épocas de mi vida están muy ligadas a la institución. Recuerdo muy bien que al lado mío, mi vecino era un ingeniero aeroespacial que trabajaba en el centro, un ingeniero sumamente inteligente y también sumamente raro, ¿verdad? Pero eso es para otra ocasión. Pero yo recuerdo que él me invitaba a acompañarle en su patio, ¿verdad? Donde tenía un enorme telescopio dirigido al cielo. Y en Los Ángeles, con todas las luces de la ciudad, de verdad es un logro poder ver la luna llena, ¿verdad? En el cielo, ¿verdad? Mucho menos las estrellas. Así que, pero con él, al lado de él, y gracias a su telescopio, yo podía mirar hasta la gran mancha roja de Júpiter y también Saturno. Así que era una experiencia maravillosa y que siempre me inspiraba ir ahí al lado de él y ver por el telescopio lo que no podía ver ni de cerca con mis propios ojos. También recuerdo que a los 10 años fui a una excursión de la primaria a JPL para visitar ahí y oír de ellos sobre una misión que apenas estaban arrancando en el momento, la misión Vikingo a Marte. Y que resultó espectacular, con grandes logros. Recuerdo que yo llegué a la casa tan animado por haber aprendido todo lo de esa misión Vikingo, que nos habían dado unos folletos y una información, inclusive unos calcomanías o pegatinas, ¿verdad? Y yo llegué a casa tan animado que pegué una de esas pegatinas en la mesa del comedor. Así que durante los próximos meses yo seguía siendo muy gran apasionado de la NASA. Mi madre no tanto, ¿verdad? Pero esa es la culpa mía. Y así que es por pura casualidad, años después, aquí me encuentro en Madrid y descubro que Madrid alberga Robledo de Chavela, una de las 3 únicas estaciones de seguimiento que tiene la NASA de naves en el espacio profundo. Las otras, hay una en el sur de California, cerca de donde me crié, y uno aquí, y el otro es en Australia. Así que no sé si irá a Australia mi próximo destino, no sé, no me quejaría, ¿verdad? Y bueno, simplemente para finalizar, entiendo que este grande edificio en que nos encontramos esconde, además de una espléndida arquitectura y decoración, como obviamente se puede ver, la leyenda de fenómenos paranormales, incluso la existencia de un fantasma. Bueno, Si fuera cierto eso, ¿verdad? Estoy seguro que ese fantasma está por aquí, en algún lugar cerca, ¿verdad? Porque debe de tanto interés como todos nosotros en Weird de James y Suzanne y lo que van a decir sobre los avances en la exploración espacial y la red del espacio profundo. Muchas gracias por su asistencia y gracias a ustedes por estar aquí con nosotros.
Well, good evening, and again, thanks for hosting us here in this beautiful facility. It really is an honor to come and just share the things that NASA and JPL are doing in many ways for the world as we explore space and explore very hard science questions. So we truly are honored to be here. Now, I think you said something about JPL and churros. I'm not sure. But I will say that whenever I'm in Madrid, I make sure I go to San Ginés to get my chocolate churros. So it's one of my favorite spots as well as my wife's favorite spots. So, and I don't know if we're strange, but there are many people at JPL who are still strange. So, but sometimes it takes that to be a smart engineer, I guess. But again, thank you for that, and I would really just like to tell you what JPL is up to in terms of exploring our Earth and our solar system and the planets and beyond, and give you a little update on all that's going on there. So first I have a little video, and this video will talk about the culture at JPL, that spirit of innovation that really drives us every day to explore and to answer those hard questions. So hopefully you'll enjoy this short little video clip.
What does JPL do?
It's the most unique place to work on Earth. Our charter is to do things no one has done before. We do what no one else even dares to dream about.
Imagination and innovation are crucial in being able to do the kind of work that we do.
Innovation comes from people, but it also, I think, comes from structure and from the environment. If you can provide people with the appropriate tools, the appropriate workspace, the appropriate environment, you're also going to get a higher innovation output.
One of the things that makes the JPL environment so special to work in is that even when you first walk on lab, it feels like a campus.
And you walk around, you hear people talking about their work.
What would be the best way to get a subsurface vehicle beneath the ice of Europa? And you're thinking, those people aren't just talking about it because they saw it on a movie somewhere. It's because they're really trying to figure out how to do it.
So I hope that gives you a sense of the people that we have and the excitement they have to take these very hard challenges and answer these very hard questions. That's what drives us every day. Just a little bit of history about JPL. We are actually a part of Caltech. California Institute of Technology really started the Jet Propulsion Lab back in the 1930s with, you see, the folks there on the left trying to understand how to build rockets. So that was the beginning of JPL, was Caltech students and professors trying to do that. In the 40s, we got into building larger rockets for the war effort to support World War II. And then when the Russians launched Sputnik, JPL built America's first satellite, Explorer 1. And you see a very famous picture there on the upper right, which is our director of the lab, Dr. Pickering, and then in the middle is Dr. Van Allen, who the Van Allen belts are named after. And then on the right is Dr. Wernher von Braun, who helped us build the rocket that launched Explorer 1 into space in 1958. So after that, the United States formed NASA. And NASA wanted JPL to be a part of the NASA organization, so we came under NASA, although we're still a Caltech organization working for NASA. And you can see there that we explore a whole lot of different areas. The Mars area, we look out into space with our telescopes. Spitzer is this wonderful infrared telescope that we've learned so much about other galaxies and planets around other stars. And we also look back on the Earth. So many people think of JPL and they think of Mars and Saturn and Jupiter, but we do a lot of science on the Earth as well, and I'll speak to that. I do want to talk about our most recent satellites that we just launched last month called GRACE Follow-On. And GRACE is a mission that is orbiting the Earth, and is measuring the gravity of the Earth very precisely. In fact, so precise that we can tell when water has been taken out of an aquifer beneath the ground. Because where there is water, there is mass. Where there's mass, there's gravity, and we can measure the change in that gravity. So for example, with our gravity measuring satellites, we've been measuring the aquifers, the water table in California for over 15 years. And you can see on the left that we once had lots of water in the aquifer in California, especially the Central Valley. And over time, red indicates less and less water. And so California has been in a drought. And we are measuring the change in the aquifer in the water table by measuring the change in gravity. So that's how we can tell how much water is remaining in the aquifer, just using this satellite. And it's a very interesting system in terms of how it works. This is a little animation. It's actually two satellites that fly together, and they very precisely measure the distance between them. So they fly about 300 to 400 kilometers apart, and by measuring the distance between them, as a satellite flies over, for example, a mountain range, there's more mass and more gravity there, and that satellite will speed up and change the distance between the two spacecraft. And then as the follow-on spacecraft comes behind it, it will speed up and catch up as it flies over the Himalayas, for example. And so we measure all those distance changes, and from that, we can measure the change in gravity. So here you can see the little animation. As we fly over a mountain, the front satellite speeds up because the gravity pulls it, and then the back satellite catches up to it. And so we can now measure with the laser measuring device we have on the satellites down to a nanometer of distance difference. So that's how precisely we measure the distance between these two satellites. So we just launched those at the end of May. We're still checking all the systems out on these spacecraft. They're replacing an older set of satellites that we had doing this same mission. And that map there shows you a map of gravity and how it's changed over time across the Earth. And we continue to monitor this. We can monitor the change in glaciers in Greenland and how they're melting. And as they melt, there's less ice, so there's less mass and less gravity. So these are some of the things we can do with our Earth-orbiting spacecraft. Now moving on to Mars. Mars gets everyone excited. How many of you saw the movie The Martian? Raise your hand. Yes, many times. We, JPL, are the only organization on the Earth that has landed successfully on Mars. So we're very proud of that. But that is one of the things we've accomplished. And so on May 5th last month, it was a very busy month for us, we launched our next mission to Mars called InSight. InSight is a mission that will explore the interior of Mars, trying to understand what is the core of Mars like, what is the interior temperature of Mars like. And so you see there on the picture that little spherical device that's sitting there on the surface. That's a seismometer, 3 seismometers that will measure Mars quakes, if you will. It will also measure if an asteroid would hit Mars or a meteorite. That will create a seismic wave that goes through the planet, and we can measure that. And based on that, we can start to build a map of the interior of Mars. So that's one of the experiments. And then I guess on your right there, that little black device that's kind of standing up, that is a penetrator. It's a device that pounds a penetrator down beneath the surface, about 6 meters. And when you're at that depth, surface temperature no longer affects the ground temperature. And so we can determine what the core temperature of the planet is, because any heat that we measure at that level has to come from the core of the planet. So those are the 2 key experiments that we have on this spacecraft that will really help us to map the interior of Mars and understand the interior of Mars, how it was formed and how it's evolved over time. So it will land on November 26th in the US. That is Cyber Monday, where everyone goes shopping online for Christmas gifts. But if you would like to watch that online on November 26th, we'll have a live broadcast of that landing of InSight. Interestingly, to get the communication back from that landing, we have satellites in orbit around Mars that allow us to relay communication from our landers and our rovers on Mars. but they're in the wrong position to relay the data when we land on Mars in real time on November 26th. So we developed some CubeSats, some very small satellites that will fly along with this mission, and they are acting as a radio relay for that entry, what we call entry, descent, and landing. So in order to get that real-time data back to us, these CubeSats will fly by Mars at just the right time, and they will transmit the information from the lander through the spacecraft, the Marco spacecraft, back to the Earth in real time. So this is the first interstellar CubeSats, or interplanetary CubeSats, excuse me.
That's next.
Interstellar is next, okay. So we're excited about that. They launched with the InSight spacecraft at the same time. We've checked them out. They're operating well, and they're both on their way to Mars right now. They're about 70 million miles from Earth as we speak. So, so far, everything is good. And now, looking at Mars and the things that we have found, you may know that we have 2 rovers on Mars. Curiosity is our large rover pictured here. Been operating now on the surface of Mars almost 6 years. In August, it will be 6 years. And really making a lot of incredible discoveries. We found organics on Mars. We found that water once existed on Mars in large quantities. There were like lakes and seas on Mars in the distant past. And just last week or 2 weeks ago, we released some findings that we found very complex organic molecules on the surface of Mars, as evidenced here, as well as evidence of methane that is impacted by the seasons. So it's a cyclical production of methane. You see there the spring, summer, autumn, winter time frame, and how it goes up in the summer and the autumn and goes down in the fall and the winter. Very interesting finding, because methane can be created by living things as they decay or as they live. We don't know what the source of this methane is. It's not necessarily living things, but it's a very exciting finding for the scientists, and we'll be doing more research on this in the future to determine what is causing that methane on Mars. As I said, we have 2 rovers that we're operating. The other rover is called Opportunity. It has now been operating almost 15 years on the surface of Mars. We thought it would last 90 days. So this is the little rover that could. I have a little video here of the Energizer Bunny, because this rover just keeps going and going and going. And you can see some of the areas we've been operating in. There's a crater there called Spirit of St. Louis we've explored. There's a valley called Marathon Valley that we've explored. Incredible pictures, incredible science, and it still continues to go until the last couple of weeks, because we are right in the middle of a global dust storm on Mars. We normally see these every 10 to 15 years. So this one just kicked off about a month to 2 months ago, and it started out in a local area pretty much where Opportunity is located, but it's now expanded to cover the entire planet. So the next slide will show Opportunity's view of the sun as this dust storm got worse and worse. So we have a camera on board on the left. You can see that what the sun looked like, and now we're pretty much in darkness all the time due to this dust storm. And because Opportunity relies on solar power, it's not getting any sunlight, and so it's not getting any power. So it's shut down, as it's designed to do when it doesn't get any power. If it doesn't get too cold, we think it will survive, because we no longer can turn our heaters on and keep things at the right temperature. But fortunately, it's summertime on Mars in this location, so it may stay warm enough to survive. It may not. We don't know yet. So once the dust storm clears, we hope that it gets power and it comes back alive. We will see. It's a mystery right now. And we don't know how long the dust storm will last. We expect at least a couple more months. It could be longer. So we shall see. So Mars is an incredible area of exploration. I'll talk a little bit about future exploration here soon. We also go out to the asteroid belt. So that's that belt of rocks between Mars and Jupiter. And we have a mission out there that is flying today called Dawn. The Dawn mission has visited the 2 largest asteroids. The second largest asteroid is called Vesta. The largest asteroid is Ceres. We visited Vesta for a couple of years, and then we then flew over to Ceres with our spacecraft, and we've been orbiting Ceres now almost for 4 years. And so very exciting mission. Looking at these, you think of asteroids as just big rocks, but these are really small planets. That's how big they are. And we've taken some incredible pictures of the asteroid Ceres. Here you can see some craters with some what we think is perhaps salty ice in the middle of that crater where those bright spots are. So there's water on this asteroid, frozen, but probably there. And in the last couple of weeks, we've changed the orbit of the spacecraft to fly lower than we've ever flown. So we're now flying about 35 kilometers above the surface of the asteroid. So I brought some pictures that show these same locations, and now that we're flying very low, the pictures we've taken now at that altitude. So you can see the fine level of detail and what the scientists can now start to look at very fine detail and do even more scientific investigation of this large planet-sized asteroid. So a lot of great data there, but again, finding the fact that ice, and then if you turn ice into water, water is there on Ceres. 20 years ago, we thought Earth was the only place that had water in the solar system. We're now finding that there's water in many places throughout the solar system, and I'll show that a bit later. This is a really cool picture on Ceres. This is an ice volcano. This is a volcano that's been formed by the pressures of the planet forcing ice up into a mountain-type structure. So underneath all that is some ice that's been forced up beneath the surface to form this volcano-looking small mountain there on Ceres. So just an incredible picture taken by our spacecraft as it orbits Ceres. And then moving out from the asteroid belt, you have the planet Jupiter, the largest planet in the solar system. And we currently have our spacecraft Juno flying around Jupiter. It was put into orbit around Jupiter in July of 2016. So it's been operating at Jupiter for about 2 years now. Its mission is to really peer below the clouds of Jupiter and understand, just like we're trying to understand from Mars, what's the interior of Jupiter like? How big is the core of the planet? What's it composed of? What is the atmosphere composed of as we look deeper and deeper into the atmosphere? So we have many instruments on board that allow us to do that and allow the scientists to gain an understanding of that. And interestingly, Juno is in a mission that flies over the north and south pole of Jupiter. And so we've never flown there before, so we're seeing these incredible pictures and videos of the polar regions of Jupiter. Everyone's familiar with the big red spot on Jupiter and those sorts of things. And we fly over that as well. You can see it in the picture there. But I just thought I'd show you an incredible view of the North Pole. Oops, there we go. So this is a video we put together from the spacecraft flying over the North Pole. And you can see all these incredible eddies and weather patterns and just a lot of things going on in the polar region of the planet that we've never seen before, because this is the first time we've flown over the North and South Pole of the planet. And again, we're the only organization that has spacecraft exploring Jupiter out that far. European Space Agency is building a mission to go out there called JUICE here in the next few years. So moving from Jupiter, I'll give you a test. What's the next planet after Jupiter? Saturn. So we also have been exploring Saturn. Our Cassini mission explored Saturn for about 12 years. Incredible pictures of Saturn, but one of the most exciting things was exploring the moons of Saturn. And we found out, remember I talked about water. Well, Enceladus, one of the moons of Saturn, we have found has water beneath its icy surface. And at the south pole of this moon, of Enceladus, there's actually cracks and fissures in the surface where this water can jet out into space. And this is a picture taken by our Cassini spacecraft of those water jets, just like a geyser in Yellowstone, shooting up into space. And over the course of the mission, we actually flew the Cassini spacecraft through these water jets and collected samples to see what was in that water. So again, like 20 years ago, we didn't think there was any water. Now we're finding water throughout the solar system in all these various moons and small moons. So very exciting. It drives us to go back and explore even more. Sadly, we had to destroy the spacecraft last September because we were running out of fuel, and we can no longer control the spacecraft if we allowed that to continue. And if we couldn't control it, there was a chance it could have collided with one of these moons in the future, and we couldn't allow that to happen because we did not sterilize the spacecraft. And so we did not want to contaminate these moons with Earth organisms which may have survived in the cold of space. So we had to destroy it, and we did that by burning it into the atmosphere of Saturn. Just like meteorites burn into the atmosphere of the Earth, we programmed it to fly into the atmosphere of Saturn. And I've got a little video clip that kind of shows an artist's rendering of those last few seconds of the mission. We tried to keep the antenna pointed to the Earth as long as we could to keep collecting data. So that was on September 15th of last year. As you can imagine, there are people who had worked on this mission for 25 years. So it was a pretty sad time for them to see their spacecraft have to end its life. But that's what we had to do. And now looking to the future a bit, we're going back to Mars. We have our InSight mission that's landing in November. We're developing our next rover that will go to Mars in 2020. It doesn't have a cool name yet, like Curiosity. We'll have a contest to name it. So we just call it Mars 2020. It's kind of an engineer thing. And so the interesting thing about this is it has a whole new set of instruments that are much more sensitive for looking for signs of life, either currently or in the past on Mars. But it will also gather samples. And we'll take these samples, these core samples, in small tubes about this big. It will then store them on the surface of Mars. And then in the mid-20s, we'll send a mission back to Mars to pick those samples up, transport them up into orbit around Mars, and then bring them back to Earth. So it's the first step in what we call a Mars sample return mission. So this mission will collect the samples, then we'll have another mission in the mid-20s that will go back and pick up the samples, launch them off the surface, and bring them back to the Earth. So that's a very exciting decade of the 20s for Mars exploration for us. Another interesting aspect of this is we are actually going to bring along a helicopter to fly in the atmosphere of Mars. And so this will be the first aerial vehicle on another planet. And we're very excited about that. This is a very challenging thing because the Martian atmosphere is only 1% of the Earth's atmosphere. Very, very thin. And so to get an aerodynamic vehicle to fly in that atmosphere is very challenging. Takes very low weight, very large rotors, going very fast. And so I've got a little picture here of our first model, our test model, our engineering model we started to build to figure out, can we actually do this? And then we put together a model that looks very much like the flight model that we'll take to Mars. And we tested it in our vacuum chamber at JPL to simulate the environment of Mars with the 1% atmosphere to prove that we could, number one, fly, and number two, control the helicopter. So this is a little video of that test that we did about a year ago. And so you can see the rotors spin up. It eventually lifts off, and it stays in control, doesn't fly all over the chamber. So we're very excited about this capability. So this is a technical demonstration just to show that we can do it. We envisioned that in the future you could have rotorcraft like this that would fly out ahead of the rover and map the path that we want to take the rover on, making us much more efficient in our traverses across Mars. And then once we send humans to Mars, we can envision a whole fleet of these flying around and examining the area around where the astronauts might land and provide further information. So we're excited about this mission to go along with the 2020 rover. It even lands safely, so that's a good thing. It's solar powered. It has a battery that powers the rotors when we're flying. We'll fly out away from the rover, for not very long, a few minutes, come back, land next to the rover, transmit our data, has a very high definition camera on board, and then we'll recharge the battery with the solar panels and then go fly again. So that's how we plan to operate the helicopter on Mars. And now coming back to the Earth, as I said, we do a lot of Earth science. You saw the gravity mission that I talked about. Looking to the future, water is a very important thing on the Earth. And so this is a mission we're building now for a 2021 launch called Surface Water Ocean Topography. This is 2 radars. You see those 2 big booms out on the side of the spacecraft. Those are 2 radars that will send a radar signal down to the Earth. They bounce back and interfere together, and we get a lot of science data out of that. So with this satellite, we can measure the height of the ocean and how it changes on average. We can measure large currents and eddies in the ocean and how the ocean is moving and working. We can measure the change in glaciers, for example, very accurately, and so on. So a very important mission for us. This is a partnership with the French space agency CNES. So we're working in partnership with them to build this spacecraft and really help our scientists understand the water cycle and how the oceans drive things and those sorts of things. And then we also have another big radar spacecraft called NISAR, NASA ISRO Synthetic Aperture Radar. ISRO is the Indian Space Research Organization in India. So this is a big partnership with India to build this spacecraft. This is also a radar spacecraft called a synthetic aperture radar in 2 different frequency bands, an L band and an S band. And as we put those 2 frequency bands together and do the radar measurements, we can measure things like biomass, how much vegetation is there in a particular area. Again, we can measure coastal changes over time and how the coast has eroded, and a lot of different Earth science information that will help us map the Earth, model the Earth, and understand the changes that are happening to the Earth. And again, on schedule to launch in 2021. So we're building that at JPL and India right now. And then moving back out to the outer solar system, I talked about the moon Enceladus at Saturn having water. This is the moon of Jupiter that also has a tremendous amount of water called Europa. Europa has an icy crust, so the surface is ice, but underneath that icy surface is liquid water. We think 2 to 3 times the amount of water that the entire Earth has. That's how much water is in this moon. So it dwarfs the amount of water we have here on the Earth. Pretty incredible. And so we're designing a mission to go out and explore that moon called Europa Clipper. We're designing that right now at JPL and starting to build the hardware for a launch in 2022 or 2023. And the first phase of that mission is an orbiter. That mission will actually orbit Jupiter and then fly very close over the moon Europa and then fly back out over Jupiter because Europa has such an intense radiation environment. We can't just orbit the moon and stay there. It would destroy all of our electronics. So we have to fly around Jupiter, come in, do a pass, come back out, and then come back in. So that's the way we'll map that moon. It has a radar that will penetrate the ice and tell us how thick the ice is. So ideally in the future we can go there and go beneath the ice and find the water. And that's the first step of that mission will be a Europa lander you see there on the right. We're designing a lander to go land on the surface after we have the orbiter there doing the reconnaissance, if you will. So potentially launching in 2026 or 2027 to land on the surface. It won't move around. It'll have some devices that can dig through the ice and take samples and measure those samples, look for signs of life, understand the chemical composition of the ice, and so on. So that's our next big mission to the outer planets, if you will. And then going back to the asteroids, I talked about Ceres and the Dawn mission orbiting that asteroid. We're now building a mission to go to the 4th largest asteroid called Psyche. This is kind of what we think the surface of that asteroid would look like. And the reason we're going there is this is an all-metal asteroid. So scientists think that this is actually the core of a planet, an all-metal core of a planet that over the billions of years, the surface was stripped away by asteroidal bombardment, meteor bombardment, and so all the soil and rock has been taken away, and all that's left is the metal core of this small planet. So now we can go there and directly examine the core of a planet with our instruments from the spacecraft. So a launch in 2022 as well as we go back to the asteroid belt. And then, of course, we talked about JPL Do and the mission we have there, the Deep Space Network. One of the things we're thinking about is currently we communicate with radio frequencies, RF. But you're limited in the amount of data you can put on an RF signal. And so we're looking at laser communication as well in the future. So on that Psyche mission, we are building an optical communication device that will use a laser to communicate back to the Earth with light at a much higher data rate than we can get with radio frequency. And so that will fly with the Psyche mission in 2022. And we envision that over time, all of our spacecraft will have radio communication as well as laser communication. And especially as you think about putting humans on Mars, for example, we know that everyone will want to have high-definition, 4K, real-time video of what they're doing, and that requires a big communication pipeline to do that. So lasers will be necessary. So for this test, we're going to bring the lasers back to our large telescopes in California, Palomar and Table Mountain. They will collect the light and allow us to get the data from the laser signal. But in the future, we want to, for example, at the site here in Madrid, on those big antennas, also add an optical capability so they can communicate either by radio frequency, RF, or by laser. And that's the plan for the future, to upgrade those antennas to be able to do that. So just kind of a quick summary. We're very busy. Many launches and many spacecraft that we're operating and building. I didn't talk about the first mission there, EcoStress. That is an instrument that can measure plant health by measuring the temperature of the plants. So plants that have sufficient water are cooler than plants that are drying out. And so this mission is going to launch tomorrow, going up to the space station, where it will be put on the outside of the space station, will orbit the Earth, and do those measurements of plant health. And again, it gives us a very good global understanding of impacts of drought and those sorts of things on our plant life on the Earth. And then the next mission coming up in the fall is OCO3. That's Orbiting Carbon Observatory 3. We have Orbiting Carbon Observatory 2 operating now around the Earth, measuring carbon dioxide. Where is carbon dioxide created? Where is it absorbed, like in the oceans or the Amazon forest? And this will also go up to the space station, and it gives us a different orbit so we can see different parts of the Earth than our orbiting satellites. So we get much more data from this, so we get a complete picture of the Earth and its carbon dioxide formation and absorption. So very important. I've talked about Mars 2020 in the helicopter. Cosmic 2 is a partnership with Taiwan that will use GPS signals to measure changes in the atmosphere as the signal propagates through the atmosphere. So a very exciting science mission there. And then I've talked about the remainder of those missions. So our job at JPL, we think, is to answer those hard science questions to the benefit of mankind. And that's what we hope you've seen here in this brief presentation. And again, it's just an honor to be here, and I will look forward to your questions after Susie's presentation. So thank you.
I get you to switch.
Let's switch seats.
Okay, thank you.
We're going to switch
Thank
seats.
you. Yeah, we're going to switch seats. So if you need to stand up and stretch, feel free to do that for a minute. Okay. So my name is Suzanne Dodd, and I'll give you a little bit of a background about me. I have been a project manager at JPL. I am currently the director for what we call the Interplanetary Network Directorate. All my non-space friends think that's the coolest title ever. But I didn't come up with it. I inherited it. But I'm extremely pleased to be here tonight to talk to you. In particular, what's involved in in my directorate is the Deep Space Network. And you have one of the crown jewels of the Deep Space Network right here in Robledo. And we've been out there at meetings for the last 3 days. Really pretty countryside, wonderful workers, just a great environment. And if you've never been there, please drive out there. They have a visitor center. It's fabulous. And it really lets you feel like you're part of the space program. And the space program is a worldwide program. And it's great. And we want to do all the outreach we can every time we come. Oh, that was the end of your presentation. Okay. So with that introduction, let's try this. Okay. Oh, so yours. I apologize. Let's see. I didn't realize. I thought they were tagged together. Thank you. I never tell anybody I'm an engineer until everything works perfectly. So.
I feel a lot better when the NASA engineers can't use PowerPoint.
That's hilarious, yeah. So at any rate, I do mean quite honestly, you have a crown jewel here just west of us. Go to the top. Yeah. Ah, perfect. Perfect, thank you. Okay. So this is not Madrid, this picture. This is in the desert in California. This is our Goldstone, one of our Goldstone antennas. But it's representative of the antennas here in Madrid. They're all the same at the different complexes. This is a 34-meter beam waveguide antenna. And what I want to do today is sort of turn things a little bit upside down from what Larry talked about. Larry talked about all the great missions we have out in space. What I want to talk to you tonight is how we use the Deep Space Network antennas as science instruments. You can actually think of them as very precise, very expensive science instruments, and that the data that comes back is key to answering questions that scientists want to answer about the planets, about stars, star formation, and it's done through these antennas, not just with spacecraft on the other end, but also by themselves. Now, I've been talking about the Deep Space Network. It's located in 3 different sites around the globe. Here in Madrid, in Goldstone, and then in Canberra, outside of the capital of Australia. If you look at a globe, those are equidistant apart. And the reason that they're equidistant apart is so that no matter how the Earth rotates around on its axis, a spacecraft way out in space, at Mars, at Jupiter, or even like Voyager in interstellar space, can always have an antenna pointed at it. So that's why the antennas are located equidistant around the Earth. The types of science that we do with the DSN and with these antennas are three different types. The first is called radio science, and essentially what you're doing is you're taking the spacecraft's beam and you're sending it through the atmosphere of a planet down to our antennas here on the Earth. And the way that beam the RF is shifted then tells you about that atmosphere of the planet. It's a very standard technique that's used with nearly every planetary mission. I can't think of one that hasn't had a radio science experiment on board. There's planetary radar. And with planetary radar, what we're doing is we're actually blasting the object with a very high uplink rate and getting the signal back off of the object. Typically, it's an asteroid. It could be a body. And we get information then on the surface and what we see. And the third type of science we do is called radio astronomy. And there we're just using our big dishes, and we're listening for certain wavelengths to gather information on chemical compositions, spectra that are being emitted by stars and galaxies or even black holes. So I'm going to talk a little bit about each of these 3 areas. So radio science basically goes back to the beginning of when we had the antennas and when we built them back in the early 60s. It became apparent that, boy, these atmospheres of these planets, they're getting in our way. You know, they're kind of screwing up. We go behind a planet, and the signal disappears, and then it comes back out again, and it changes things, and that's awful. But really, what they found out is that's science, okay? One man's tragedy, is another person's science. And we use this property where we have a signal pointed at the antenna here at Earth. We let the spacecraft go behind, that signal disappears, then it comes back out. That's called an occultation. And by doing those occultations, we get all sorts of information on the atmospheres of Mars, Saturn. The Voyager missions used it at all the planets, Jupiter, Saturn, Uranus, and Neptune. And it's one of the ways to study the atmospheres of planets. We can also use it, though, to study the interior of planets. And the image here is an image of Cassini and Enceladus. General James talked about Enceladus and how it has the jets of water that we think are coming out. So the Cassini mission used the signal and the changes in the signal as it sent it to Earth to determine that, yes, there is actually a subsurface ocean under the surface of Enceladus, and we saw the jets there too. It's a demonstration of how a spacecraft and the DSN together are one instrument. Now, the way radio science also works is it can measure gravity fields, and that is very simply the same way the GRACE follow-on mission works. If your spacecraft is going over a mountain, it's going to be pulled toward the body, toward the planet in this case, or if it goes over a valley, it'll be pulled back toward the Earth. And the change in the signal then allows you to map the gravity field of the planet. So that's another way that radio science works by mapping gravity fields, as well as previously we were talking about mapping atmospheres. So the missions that are involved with radio science today, some examples of them include, as I mentioned, Enceladus, and the first evidence of the subsurface ocean that Cassini found. And Enceladus is going to be a target that we want to go to in the future. The scientists are planning how we're going to go back there, how we're going to orbit it, how we're going to measure those geysers and really see what's under the surface of it. We've also done, with the New Horizons missions, measurements of Pluto's atmosphere, where we've seen how the pressure and the temperature of the atmosphere can be coupled with the surface composition. New Horizons was the first planet to actually fly by Pluto, and they got great data, and they're continuing on out to the asteroid belt now as we speak. If we look a little further, the Juno mission at Jupiter, it can use radio science, again, to study the composition and underneath the surface of Jupiter. Jupiter is a gigantic gas ball, right? So it's primarily all gas. So as that signal changes and how the gravity pulls and pushes on that signal as it goes around a planet helps us have better information and develop models on the compositions of these giant gas ball planets. And we look at those to see how they relate to exoplanets or planets around other stars. What's the theory behind the creation of giant gas planets? And how do what we see in our solar system match what we're seeing now as we're discovering all these other solar systems out there and all these other exoplanets? Finally, again, we talked about using radio science to map gravity waves, or map the gravity field of a body. This happens to be Sirius. The images on the left is pretty much optical. The one on the right, the colored one, is a gravity map of Sirius taken by the Dawn mission. And so you can see the areas in red are primarily the heavier mass, stronger gravity than the area in green. And so we're able to map out the gravity fields of these planets and bodies as well. So in the future, what are we going to be doing with radio science? As I mentioned, it's basically on every mission. It's almost a freebie, right? You got to get the data back to the Earth. You got a big antenna on the Earth. It's like a freebie with the mission. So there's a ESA mission that's launching in October. It's going to Mercury. It's in the process of going to Mercury, though. It's going to be using the radio science to test Einstein's general theory of relativity. And that's something that we're looking forward to. It's something that the Deep Space Network here will be supporting under our cross-support network, even though it's not a NASA mission. We do support missions that are not NASA missions. Again, we've talked about the Europa mission. And I think radio science is really going to be key for Europa in order to understand what might be under the surface and what the gravity pulls and tugs are on that body. If we look at future missions to ice giant planets, here this is Uranus on the left and Neptune on the right. We'll try and think about how we could use radio science to, again, help us talk about what is in common between the ice giant planets and what's not in common between them, and how are they formed, and again, how do they relate to the exoplanets that we're now discovering with things like the Spitzer Space Telescope. And finally, we'll get to a point where we want to have more probes go in these atmospheres, similar to the probe that went through the Galileo atmosphere. You can imagine a fleet of probes going down through the atmosphere, sending signals back to an orbiting spacecraft and looking at those signals and being able to see the shift in the signal to determine both the composition or the thickness of the atmosphere and wind speeds and things like that at the different layers of the atmosphere. And so we're looking at those type of missions both for Venus and for Mars, our closer planets, which we know have atmospheres, and looking at possibly dropping probes through those atmospheres and then using the radio science technique to get more discovery on the atmospheres. Now, the second type we talked about, or I mentioned, was that we do radar with the DSN. So in this case, radar does not involve a spacecraft. Radar involves a very strong signal, about a 500 kilowatt uplink signal, and we blast the signal out of the DSN. It gets reflected off of the body, and the DSN sees it on the way back. And that reflection and the shape of the reflection then can tell you what the shape of the body is that you're looking at. A normal transmit to a spacecraft is about 20 kilowatts. So we're talking about 500 kilowatts here. So quite a bit stronger a signal. And what's important to realize is that radar is often the beginning study of an object. And radar has really led to billions of dollars of spacecraft missions to go to that object. The first radar observations of Venus occurred in 1962, when it made a discovery of a retrograde orbit of Venus. Well, the Magellan mission then went there in the late 80s and did a mapping of the surface of Venus. Similarly, we've done radar of Titan back in the 80s and 90s that suggested that Titan would have maybe a methane surface on it. So when Cassini got there, Cassini had used its antenna as a radar, bounced the signals off of it and back to the spacecraft, and got these fabulous pictures that you see here of the surface of Titan using radar. We've also looked at Mercury and discovered through the radar and then later through the Messenger mission that there was polar ice on Mercury that we didn't think of before. So radar is really a discovery tool, and it just uses, all it uses is the DSN on the ground. I would say in particular, one of the things we use radar for is to look at asteroids. You know, we can look at objects not too fast moving, but reasonably fast moving, going through our solar system to map them out. It's very easy with radar to look at the size, the rotation, the density, surface features, all of those things that you would want to know about an object that you knew nothing about. We have a program at the Goldstone station that's called the Goldstone Solar System Radar. So it's a specialized radar. It's on the 70-meter antenna, and it's used by scientists. They propose to it. They get time on that big antenna to do radar of specific objects. The importance of radar is not just for the science, though. We also will have humans in the future up in space. We need to be able to understand what the objects are, how likely they are, how close they will come. So we do a lot of mapping and surveys of objects. And there's even a department at NASA called Planetary Defense. Sounds really cool, right? So the idea behind Planetary Defense, though, is to look for hazardous asteroids, ones that might hit the Earth. And is there any characteristics that are similar between those? That type of stuff happens. That lower left-hand picture is the meteorite that came through Russia a few years ago, right? And everybody's dash cam got a picture of it. And those are the type of things we're looking for. And it's both for scientific reasons as well as understanding what might be coming at us in the future and how we could protect our astronauts as well as us here on Earth. One interesting thing about asteroids is that almost 15% of them have a binary object. They have a moon. And almost all of these binary objects, because they're small, have been detected through our radar and our Goldstone radar program. And you can get a comparison here. This is the object Enceladus, the asteroid. With our DSS-14 antenna, we get a 3.75 meter resolution from 7 million kilometers away. It did take 65 hours of radar time to take the image. But you can even see in that image on the lower left, you can see that you can not only the asteroid, but you can see features on the asteroid. So on the right is a Chinese spacecraft, Chang'e 2. It has an 8 meter resolution, so ours is actually a little bit better resolution. But theirs was taken from 18.3 kilometers away, not 7 million kilometers away. And it only took them 15 seconds, not 65 hours. But when you look at the objects, you can, you can see how you can really compare the radar, the ground-based radar, with a space-based observation. And again, I go back to the point that the ground-based radar is often one of the first science data that you get that then tantalizes scientists to want to take a spacecraft there and promote a mission to go there in person. The last type of science we do with the Deep Space Network is called radio astronomy. And this is where we're listening. We're pointing the antennas at a star, at a galaxy, at a nebula, and we're listening in certain frequencies and wavelengths to what data is getting back, the spectrum that we're getting back. In particular, this example is actually the project is here in Robledo. It's done with the Deep Space Network Madrid site. It's done by a Spanish PI. And he is studying the star and the nebula that's around the third star in Orion's belt, if you're familiar with that constellation. And so he's looking at the chemical composition of what's called Orion KL and the emission lines that he can see through using the antenna here on the Earth. If you recall from your basic astronomy that stars eventually explode. They die and they explode. Some stars, not every star, but some stars die and explode. And this is just an example of a supernova and an explosion. So out of that explosion comes the material and I want to say goodness, but basically new stars are formed out of old stardust. So the nursery for new stars is from the explosion of old stars. And when we do our radio astronomy, we can look at these old exploded stars and do basically interstellar chemistry. And this is another example. There's a Spanish PI involved with this, where they discovered, using radio astronomy, a new, basically they debunked a theory where they thought that stars should produce a certain amount of helium-3. And when they looked at the star field, they saw that it only produced 1/3 of what they thought. And scientists are always testing their theories. And this is actually, it's a ground-based, inexpensive way to do science in radio astronomy and look at compositions of stars and galaxies. I like talking about black holes. They're really cool. People think black holes are really cool. So we do radio astronomy with black holes also. Every galaxy is going to have a black hole basically at the center of the galaxy. And this particular galaxy, NGC 4293, has a black hole. And we're doing a survey with the large antenna, the 70-meter antenna right here in Robledo, to look at that black hole. We can determine from the signals we get back and the wavelengths we get back, we can determine the spin of the black hole. We can also determine what's getting ejected out the black hole, what the chemical composition of the black hole is. And it's really quite exciting. And I think it's important to remember that you can do science with the ground-based antenna. It's not just about catching the science that's coming back from the spacecraft. You can actually send signals up and retrieve signals, and that antenna is the science instrument. It's not your garden variety television signal, high definition receiving antenna. They're very sophisticated and really very important to the scientists. And I think all the folks that work there and all the people in Madrid that are involved with the Madrid complex should be very proud of yourself. You are providing science to the world. You're a big piece of this. And it's extremely unique, and it's very important for us to understand the universe as well as, it helps us then reflect back on ourselves and the science processes that go on here at Earth. Just to point out to you, we do have a website, and it's called eyes.nasa.gov.dsn, and you can see what each of the antennas is, which mission they're tracking at any time of the day or night. So the 3 sites with Madrid on the top, Goldstone, and Canberra. This is an example where the Canberra antenna, the 70-meter number DSS 43, is actually doing a ground-based astronomy. And we schedule these ground-based astronomy passes with the antennas in amongst all the passes that we have with the various missions we track. The actual percentage of time that's spent on ground-based astronomy is, I would say, less than 5%, but it is really important. And people often forget that we do science with the antennas. And so, part of my job here tonight is to tell you that we do science with these antennas and to impress upon you that that's an important role that these deep space network sites do. So with that, I want to say gracias, Robledo, Madrid. You have a science instrument here in your backyard, and you should be very proud of it. So thank you very much.